So we're going to talk about matter. And in this video specifically, we're going to talk about physical state, since it's one of the most common and easily recognizable properties of matter. To start with, what do we mean by matter? A classic textbook definition of matter is anything that has mass and takes up space. Takes up space, that's the same thing as volume. So anything that has mass and volume is matter. You might say to yourself, well, that's everything. Pretty much. It's mostly everything that you can experience with your senses. However, there are things like light, electromagnetic radiation, things like gamma rays, for example, heat. Those things you can experience with your senses, but they don't have mass and they don't take up any space. Light doesn't take up any volume, and it certainly doesn't have any mass. So that's not matter. That's energy. Okay? We're specifically going to be interested in things that have mass and volume. That's what matter is. We already know, because of the work of John Dalton, that all matter is composed of tiny little particles. We call them atoms. More specifically, we say that matter is made of elements and or compounds. Okay? There are three main physical states. Technically, you can say there are four. We'll talk about the fourth physical state. But really, I want you to be familiar with the characteristics of solids, liquids, and gases. Okay? So we'll start with the physical states. What determines a substance's physical state is how its particles, how its atoms or its molecules are moving, motion. All right? And the energy that moves them is called kinetic energy. So everything has kinetic energy. The more kinetic energy you have, the more kinetic energy a system has, the faster those particles will be moving, and that will determine whether it's solid, liquid, or gas. Okay? The way we measure kinetic energy is temperature. Now, here's a distinction I want you to be very, very clear on. Temperature is not a measurement of heat. It's a measurement of kinetic energy. And that's very, very important. They are not the same thing. Heat is a different type of energy than kinetic energy. Kinetic energy is motion of particles. Now, heat can be converted into kinetic energy. Heat can make particles move faster. But what we measure when we measure the temperature is the motion of the particles, not the heat. That's important. Okay? This concept of temperature then is based on the idea that there is a point at which there is no motion. That would be no motion, zero. And Lord Kelvin was the guy that came up with this idea. And he said there's a point, we'll call it absolute zero. Absolute zero, zero kelvins. That's the point at which motion stops. It's theoretical. We've never reached it in a laboratory or anywhere. Because of the way heat moves, heat transfers, and heat turns matter into, or turns particles, gets them moving. And so there's really no way to get to absolute zero. But in theory, it exists. And in theory, it's about negative 273 degrees Celsius. You already knew that, though, because you already know how to convert from Celsius to Kelvin or vice versa. So when we measure temperature, we're talking about measuring the amount of kinetic energy. So if you increase the temperature of something, you're increasing the motion of the particles. How do you do that? Well, yeah, you add heat. But remember, temperature is not measuring the heat you're adding, it's measuring what it's doing to the particles. Okay? If you add enough kinetic energy to matter, you will get its particles to move fast enough that they will change physical state. That's all you're doing, is you're making them move fast enough that they change how they're relating to one another. So let's take a look at what we mean by that. So for solids, let's start with solids. The particles of a solid are in fixed positions. Okay? Their position is fixed. They can't move out of that position. Now, that doesn't mean they have no motion. It just means that they're stuck in place. Why? How can they move if they're stuck in place? We'll get to that. Okay? That means because that their particles of a solid are stuck in a particular position, that means that the shape of a solid is definite. You can determine the shape of a solid, and it has a definite volume. Okay? So those two things are a result of the fact that the particles are not moving very much. But they are moving. Even though they have a very low kinetic energy, low amount of motion, they are vibrating. So the analogy that I like to use, if you think about yourself sitting in a classroom somewhere, you are stuck in a position, you're in a desk, but you're not immobile. You're still moving around a little bit. You're wiggling back and forth, you're stretching, whatever. That's the type of motion that we have with particles, except it's vibrational. They vibrate. And the frequency of those vibrations can be determined actually pretty easily. There are two types of solids that you want to be aware of. The first is called a crystalline solid. Crystal is a word that means a pattern or order. And so crystalline solids, the solid particles, yes, they're fixed in positions, but those positions are very, very regular pattern or order. Okay, so crystalline structures are very ordered. They have three-dimensional structure. They're very beautiful when you see them in large pieces. You've seen crystals, you know what they look like. The other type of solid is called an amorphous solid. The word amorphous, morph means shape. And when you put the prefix a in front of it, it means without. So amorphous means without shape. Those particles are arranged randomly, and it doesn't really matter where they are. They don't have any pattern or any discernible order to them. Okay, glass is an example of an amorphous solid. The particles in glass are stuck in any random arrangement, and so that means glass has various shapes that you can put it into, depending on how you let that glass harden. Okay. If you have enough kinetic energy added to your solid, you can break those fixed positions, and that's called fusion. We commonly call it melting, but its technical term is fusion. Okay? Liquids. Well, in liquids, the particles don't have a fixed position. They are still in contact with one another. They're close enough to touch each other, but they're not stuck in any one particular place. Well, that means that a liquid doesn't have a definite shape. It'll take the shape of whatever container you put it in. But it does have a definite volume because the particles are still touching each other. Okay? It has a moderate amount of kinetic energy. The particles are moving, and so they slide past each other. Think of it as if you're trying to move through a very crowded room. You're kind of touching people, and you're not going to get through very fast, but you can move. You can move around. The particles of a liquid are held together. They're held in contact by something called intermolecular forces. Let's break that word down. Inter means between. Intermolecular means between molecules. So forces that are acting between these molecules. We're going to go into those in much greater detail later on. But that's what holds the liquid particles together. Certain liquids have strong intermolecular forces, or IMFs. IMF is what we call it. And other liquids have very weak IMFs. And so that's what holds them in contact. And that means that if we want to break them apart from each other, if we want to cause the liquid particles to separate, we have to overcome those IMFs. If we can do that, we can add enough energy to get the particles to move a little faster so that they actually break contact with each other. That's called vaporization. Commonly, we call it boiling. I don't like to use the word boiling because it implies a high temperature. And in fact, any liquid can boil at any temperature. It just means you're separating the particles and getting them to move around faster. So something like methane, for example, or carbon dioxide, or gases at room temperature, they boil when they're liquids. They just boil at really low temperatures. So I like to say vaporization, but boiling is what's happening there. For a gas, now we have particles that have no fixed positions. They can move wherever, and they're very far apart. They're not touching each other. The reason that they're doing this is because of a tremendous amount of kinetic energy. Well, that means that they don't have a definite shape, for sure, but they also don't have a definite volume. That means gases not only take the shape of the container they're in, but they also take up the entire space you put them in because of how these particles are moving. They're very, very fast motions. Because they're moving so fast, because they have so much kinetic energy, they will hit each other. They'll collide, and they'll collide with surfaces. They'll collide with anything in their way. And when they do that, there's a transfer of energy that happens there, and that's what we're going to talk about when we look at pressure, gas pressure. Because gas particles are far apart, they're not touching each other, and they're moving very fast, any more energy that you add isn't going to do anything else to those particles, except at some point, if you add enough, it's going to cause the electrons of those particles to fly off. They're going to become ions. That process is called ionization. Okay, so if you increase the temperature of a gas, at some point you're going to get that gas to ionize. And when you do that, you form plasma. And that's the fourth state of matter, is a plasma. It behaves differently from the other states. It is technically a gas because the particles are very fast moving and very far apart, but it's very hot because that's how you get the electrons to leave. And it's ionized. The particles are ions. And we're talking, when we say hot, we're talking thousands to millions of degrees to get this to happen. So they're really, really, really hot. Okay, generally, when we're talking about full plasmas, that's what we're talking about. They're very reactive. because they're made of ions. Those ions are not electrically happy. They want to become stable again, so they'll look for things to combine with. And because they're charged, they're affected by electric and magnetic fields. And we see a lot of plasmas in space. The sun, for example, is a plasma. There's a lot of hot ionized hydrogen and helium gas going on there. And there's other stuff going on in the sun, but you can see the plasma there. There are plasmas, a lot of the matter in the universe is plasma-based. And so they actually, not only are they affected by electric and magnetic fields, but they also create these electric and magnetic fields. Plasmas glow. And we'll talk about what causes them to glow, but it generally has to do with the fact that when electrons leave an atom, they take energy in, and when they come back to an atom, they give energy out. And then we want to look at the difference between full and partial plasmas. A full plasma is really completely ionized. Partial plasmas aren't necessarily as hot. You can create a partial plasma by ionizing a gas with electricity, for example, and it'll still glow. It just won't be as hot. So when you look at things like neon lights are gases, neon, that has been ionized partially, and the ionized part of that gas will glow, and you get that bright red glow. Okay, so those are the states of matter. We change between them by adding heat, by creating more kinetic energy. And so the terminology that we use, again, if solid is going to a liquid, we call that fusion, commonly melting, but again, we like fusion instead. If a liquid goes to a solid, in other words, if we take away kinetic energy, we remove motion, it becomes a solid, we call that solidification. Now, I put the word freezing in quotes because when you say freezing, you think about a low temperature. But if you think about something like lead metal freezes at almost 1,000 degrees Celsius. 1,000 degrees is not cold. So we say it solidifies. It turns back into a solid. Okay. Liquid going to gas, we call it vaporization. We talked about the difference between vaporization and boiling. The opposite way is called condensation. So when gas turns back into a liquid, it's called condensation. And then there's a third change that we want to look at. And that's when a solid goes directly to a gas. When a solid goes directly to a gas, it doesn't melt, it just turns into, it vaporizes. We call it sublimation. We say the gas sublimes. An example of a substance that does this very well is dry ice. Dry ice is solid carbon dioxide. Dry ice does not melt. That's why it's called dry ice. It's solid, but it immediately turns into carbon dioxide gas. And that's because the intermolecular forces between the carbon dioxide molecules are very weak. It doesn't take very much to get the molecules to go out of their fixed position and just turn back into a gas. The opposite of sublimation is called deposition. A solid will deposit on a surface. And it's all based on the amount of kinetic energy and how strong the intermolecular forces are. All of those transfers. Okay? So that's the nature of physical state. It's all about particle motion. Make sure that you understand that, because later on when we talk about, well, how does that affect the behavior of molecules, you'll want to come back to this video and remind yourself about the nature of kinetic energy and motion and what that does to particles, especially when we start talking about gases, because the behavior of gases is almost entirely based on this.